Okay, so there are like 5 different objectives that I want to teach you. So you can see these in the book as well. But the first one is, I'd like to teach you how to convert between decimal degrees and degrees, minutes, seconds. Is it okay if I use red? Is anyone going to have trouble reading that? Okay. The second objective is how to find the arc length of a circle. So how to find the length of an arc on a circle. Okay, how to find the length of an arc on a circle. Okay, third one is how to convert between degrees and radians. Some of you have heard of that before. Maybe your only exposure to radians is you pressed mode once on your calculator and you saw that there were choice between degrees and radians. So we'll finally talk about that today. 4 is how to find the area of a sector and the last one is understand the relationship between linear velocity and angular velocity. So I know that's a lot to write, but I assure you each skill is very simple. There's just a lot of them. Okay, so let's get started with objective 1. Okay. All right, our first objective is to talk about degrees, minutes, and seconds. So you guys know that an angle is actually just 2 rays, right, that share an endpoint. So this is called an angle, as you know. This is the point called the vertex, but this is really just 2 rays. Okay. And if I told you that I wanted you to draw a 1-degree angle, you would draw something like, oops, probably something pretty small, right? 1 degree? Wow, that's like really tight. That might be 1 degree right there. I don't know. I'm not going to get out a protractor. But you guys know what I mean. It's a small angle, right? 1 degree. Is 1 degree small? It kind of depends, right? It depends on how close you are to the vertex. If you're very close to the vertex, this space is real tight. But as you go further out from the vertex, this space seems to widen up. If I told you that your job was to travel from here to a point across the street, and you actually made a path, and you were supposed to go over to the fire hydrant there, and you were off by 1 degree, right? You might find yourself maybe a few feet from the fire hydrant, so you missed your mark a bit. But if I had you going from here, let's say, to your home, and you charted it out, and you're off by 1 degree, chances are you're going to end up in someone else's house, right? Or if you're an astronomer, or an astronaut, let's say, and you wanted to travel from, I don't know, here to the moon, and you're off by 1 degree, you ain't going to the moon. Okay, 1 degree exaggerates over distance, right? So you're going to be way off. So 1 degree is not that accurate of a measurement for someone studying large distances, you see? So we need something smaller than a degree. So what's smaller than a degree? Half a degree? 1/10 of a degree? Okay. Can you have an angle like 0.9 degrees? You can have that, right? Maybe you've done SOHCAHTOA before, right? And you did an angle in a triangle and you found out that it was, 37.28 degrees. So you can certainly have decimal degrees. The problem is there's this old navigational type system that is used, and it's still used, and it looks like this. 1 degree contains 60 minutes. Or some people write 60 apostrophe. 1 degree contains 60 minutes. What we're saying is, if you took this 1 degree angle, which is already quite tight, and you split it into 60 equal parts, they would be so small, right? Very minute. They're called minutes. Okay? Each one's called a minute. Just like we can take an hour and break it down into 60 minutes. We can take 1 degree and break it down into 60 tiny angles called minutes. I would draw that for you, except you wouldn't even be able to see them. They're so small. And my pen is so thick, so it wouldn't work very well. Can you at least imagine splitting this into 60 parts? This angle here? Okay, maybe you can, maybe you can't. Imagine if you took one of those tiny, tiny little parts and split that into 60 parts. 1 minute contains 60 seconds, also known as 60, and then just a traditional little quotation mark there. So you might be saying, hold on, Mr. Shar. I know that an hour has 60 minutes, and I know that 1 minute has 60 seconds. When we're talking about time, well, it's the same system being used for a degree instead of an hour. So an hour contains 60 minutes, and so does 1 degree. So they mean like little tiny angles. And a minute contains 60 seconds, both in the time world and in the angle world. Weird system. I mean, who measures anything out of 60 anyway? 1/60th, 2/60th, 3/60th. Nobody does that, right? Well, back in the day, that wasn't so strange to people. A long time ago, the Babylonians and the Hebrews used a calendar with 360 days. Do you think it's a coincidence that there's 360 days in a Babylonian calendar and 360 degrees in a circle? That is no coincidence. Okay? Somehow the 60s and 360s and that sort of thing all kind of made its way into the 21st century, so we're still using this. Weird. Okay. Let's just write down a few facts here, okay? So what we're saying is, another way of saying this is 1/60th of a degree is 1 minute. And 1/60th of 1 minute is 1 second. Or you could say 1/3600ths of 1 degree is 1 second. So what I'm saying is we can also add a statement up here. 1 degree contains 3,600 minutes, or seconds. Just like an hour contains 3,600 seconds. Now, if you've never heard of this, it's because you're not a pilot, or you don't draw maps for a living, you're not a cartographer, okay? You probably don't look on Google Maps that carefully, where you've checked latitudes and longitudes, and sometimes angles are written like this. You're probably more familiar with things like 45.28 degrees or whatever. Well, let's talk about that real quick. Let's say someone gives you an angle, so here's our example, and asks you to convert it to decimal degrees. The angle I chose is 45.28437 degrees. I would like to convert this to something I understand. I'm sorry, I think I'll do it the other way first. That is decimal degrees. Sorry, I meant to do this. We'll do that example in a minute. We're going to convert that to degrees, minutes, and seconds. I want to convert this sort of cryptic statement into something I understand better. What does this mean? 45 degrees, 15 minutes, 22 seconds. It just means a little more than 45 degrees. Okay, so it literally means this. It means 45 degrees plus another 15/60ths of a degree plus another 22 3,600ths of a degree. That's what it means. Okay, so for this you need a calculator, right? So you pull out your calculator, and I'd probably let you need to use a calculator on this problem on a test, right? Otherwise you'll have to suffer the wrath of long division. Okay, so this comes out to be 45.2561, repeating, degrees. Okay, that I understand better. That just means something between 45 and 46 degrees. So I would prefer to write it like this. This is called decimal degrees. But if I was a pilot or a ship's captain or an astronomer or something, I might prefer this system here. It's the same thing. It's just a different way of looking at the angles between 45 and 46, you know. Okay, so how do you convert from DMS, degrees, minutes, seconds, to decimal degrees, DD? You take the minutes and divide it by 60, you take the seconds, divide by 3600, and you add it all to the whole number of degrees you have. Pretty straightforward. Okay, now let's go ahead and do it in reverse. So let's say I gave you convert 9.6042 degrees to degrees, minutes, and seconds. Okay, so we already know that our answer is going to look something like this. You can actually just kind of box it right now. Okay? That's what I usually do. I just draw my answer. I already know that it's 9 point something degrees, so that means it's at least 9 degrees, and plus there's some other junk left over. But what do I make of this 0.6042 bit? Well, remember we took the parts and divided by 60 on the previous example, so we'll be taking this and multiplying by 60 on the calculator. This will help us figure out how many minutes we have. My calculator says 36.252, and don't round it, okay? Don't round it. The whole point is to get accuracy. That's like the whole reason we're doing this. Tiny angles, nice and accurate. What does this mean? This means 36.252 minutes. So now I know that there's 36 minutes. So that goes here. What am I going to do with this 0.252 minutes? I'm going to multiply by 60 again to figure out how many seconds that is. Not 3600, by the way. All right. So 0.252 times 60 again is 15.12. This represents how many seconds I have. And so I have 15.1. I'll just do 15.1 seconds. The difference between 15.1 seconds and 15.12 seconds is so tiny. I mean, we're talking about being off by 1% of 1/3600th of a degree. So I'm not going to quibble about the 0.12. If you want to put the 0.12, go for it. Okay? So that's how you convert from degrees decimal to DMS and back again. Just be careful right here. In this first example, you had to do a 60 and a 3600, but in this you only use 60 and you use it twice. So there is a 3600 working in here, but it's when you multiply by 60 twice. So don't multiply by 3600 on the second type of problem. Okay, just follow the notes carefully when you do your problems. Okay, let's go to our second objective. Finding the length of an arc on a circle. Finding the length of an arc. Okay, so you actually did this in geometry class. Okay, what was going on was your teacher drew a circle for you, right? Drew a radius. they had a central angle here. We call this a central angle. This is the radius. This might be called like central angle in your geometry book, right? Central angle. And this distance might be like arc AB, you know. And so your teacher would say something like this: let's find the length of that arc. Well, it's actually very, very simple. You can use your common sense. You don't have to take a geometry class to understand a lot of basic geometry. AB is partway around the circle, some fraction of the full circumference. So isn't it true that the length of arc AB is just some fraction of the circumference, 2 pi r? The question is, what fraction? Well, if the central angle is 180, then it's half the circumference. If the central angle is 90, then it's a fourth of the circle. You know, if the central angle is 1 degree, then it's 1/360th of the circumference, you see? So this is just common sense. You would just take your central angle divided by 360. This tells you what fraction of the circumference is red, see? And then you just times it by 2 pi r, which is the full circumference, and it gives you the part of the circumference. It's so simple, and I'm sure your algebra or your geometry honors teacher actually wrote this formula or was in your textbook and you used it. You probably didn't think about what it meant at the time, but it's just common sense. It's a fraction of the circumference. Maybe they made it challenging by reducing the 2 and the 360, so it looked like a 180 there. Maybe that's what threw you off. Maybe you didn't realize it was that simple all along. Okay, we're not going to be using this formula at all. Okay? We're going to be using one that looks like this. S equals r theta. This is pronounced theta. It's a lowercase Greek letter. Okay? There's a couple reasons we're using this formula instead of the one up above. One is it's simpler. You guys like simple formulas? Yeah. Another reason is it uses angles not measured in degrees, but angles measured in radians. And you might not be a fan of radians when I explain to you in a minute what they are, but you will be later if you take calculus, because in the world of calculus, degrees makes life very complicated. And radians makes life very simple, relatively speaking. So you might not like radians yet, but you will. This formula is going to be our preferred formula. If you must use the one up above it, fine. Okay? All right, so let's talk about what the variables mean real quick. S is the length of the arc. So we kind of stopped using the little arc AB notation that you used in geometry class. So goodbye A, goodbye B. We now call this just plain S, but it means the curved distance on the edge of that circle. R, of course, means radius. It's always meant that. Okay, so nothing new there. Radius of the circle. And theta, like many other lowercase Greek letters in math, represents an angle. Okay, so oftentimes when you see a lowercase Greek letter, it's referring to some angle. So this is your central angle. And I'm going to put a little warning here. It must be measured in radians. Which brings us to our third objective. This angle must be measured in radians. Now, we're going to come back to this and we're going to do some examples of this, but we can't until we talk about radians. So we're going to take a little detour, leave some space here for some examples, and let's go to our third objective. Third objective is to convert between degrees and radians. Okay, so you might wonder, what is a radian? Well, that's like a person living in Korea who might say, what is a foot? What do you mean by a foot? We don't measure in feet here. We measure in meters, right? Well, you'd have to explain to them, well, foot's like about that long. You know, there's 3.28 of them in one of your meters. You know, and then if you used yards or acres or other things that are from the imperial system, you'd have to explain all that stuff, right? Well, here I am explaining what a radian is to you. But in the world of math, radians are used sometimes, like I said, more often than degrees are. So what exactly is a radian? So here's how it works. Let's say you were given a circle, and the radius was simply 10 inches. And you decided to start on the edge of that 10-inch circle and draw a 10-inch arc. Okay? You would end up at a point right here, let's say. And you might wonder, I wonder how many degrees I just traveled. It's a good question. Okay. Someone else maybe is dealing with a larger circle, maybe radius 20 or something, and they have the same question. Okay, so they have the same situation exactly. This radius is, let's say, 20, and they draw a 20-inch arc on their circle. They end up at a point, say here, and they ask, I wonder how many degrees I just traveled, you know, in the central angle sense. Well, it turns out that both of these traveled the same angular distance. They all traveled the same angular distance. So the number of degrees that they came through, they subtended, is the same. This is congruent to this. All circles are similar, right? Okay, so how many degrees was it? It turns out it's right around 58, 57 degrees. Okay? But because this situation is fairly unique, and it's kind of a special situation, this has been called 1 radian. 1 radian. So what is a radian? A radian is the amount of angle you get when you travel along the edge of a circle by the amount of your radius. Interesting. So who came up with that idea? You know, it's kind of a weird one. But it turns out it makes things very, very simple later on. Okay, so if this is the case, and if 1 radian is close to 60 degrees, I wonder how many of those slices it would take to fill a full circle. How many slices do you think, if this was a pizza, and I cut out a 1 radian slice, and I tried to share it with people, how many slices do you suppose I could split this up into? About 6, right? I said that a radian is about 60 degrees. There's 360 degrees in a circle. Okay, so it turns out we can figure out exactly how many radians there are in a circle by just using a direct proportion. If traveling a distance of 10, right, along the edge of the circle, if that produces 1 radian, central angle, then by direct proportion, what would happen if I went all the way around the circle? 2 pi r. How many radians would that be? See? Or you could apply this to the second drawing if you like. Well, if you solve this for x, you get 2 pi. What does this mean? This means once around the circle is 2 pi radians. 1 revolution, 2 pi radians, 360 degrees are all equivalent. Okay, so if someone says, hey, I just went once around the circle, you can say, oh, you went 2 pi radians. Or you can say, oh, you went 360 degrees. Same thing.
Just for that specific circle?
No, it's true for any circle. What happened was, if you traveled any distance along the edge that's equal to the radius of the circle, either way this r would have canceled out and I would have gotten 2 pi. So it turns out that all circles have 2 pi radians, just like all circles have 360 degrees. All right, so there's lots of ways to memorize this. You can say that 2 pi radians equals 360 degrees. You can say that pi radians, therefore, is 180 degrees. Okay? You can memorize that kind of stuff. Let's try an example. Let's say someone comes up to you and says, my teacher told me to draw a 2 pi over 5 degree angle. But I don't even know what that 2 pi over 5 radian angle, I don't even know what that means. So you would want to convert that to degrees so you can understand it better. If I said, everybody come on, draw a 2 pi over 5 angle, go, go, ready, go. You got 10 seconds. You might be like, what? Well, it means 360 over 5. That's what it means. So it means a 72 degree angle. So you just grab your protractor and draw it. Okay? Which means if the problem said convert pi over 6 to degrees, you wouldn't treat pi as 360. 2 pi was 360, right? Pi represents 180 is what it really means in the world of degrees. You would say, oh, that's just 30 degrees. So you could just think of pi as 180. Just replace the pi with a 180, and you've got degrees. Even if it's a tricky one like this one, convert 3 pi over 17 to degrees. Yeah, it looks trickier, but all it means is we're going to try to replace the pi with a 180. By the way, mathematically, when you replace pi with 180, it looks like this. You divide by pi to get rid of it, and you multiply by 180 to replace it. Just grab your calculator and multiply by 180 over pi, see? So let's try that. What's 3 times 180 divided by 17, I meant, not pi. This means 31.7647 degrees. So since we're so used to thinking in degrees, if you're given a radian measure, you can just multiply by 180 over pi, and that will help you decide what it means. What if we switched up the question and I said, convert 22 degrees to radians? Okay, this is a little bit harder to think about, but listen, if multiplying by 180 over pi is how we go from radians to degrees, then wouldn't it just stand to reason that multiplying by pi over 180 would take us from degrees to radians? Okay, so that's all we're going to do. We're just going to multiply. This is degrees. We're going to multiply in such a way as to get rid of degrees. So you would want to put the pi on top and the 180 degrees on the bottom. This way, degrees is removed from the problem. And you can just write it as 11 pi over 90 radians. Or you can get your decimal going on that. 11 pi over 90. I'm no savant, so I'll type it in. 0.384 roughly radians. Is that small? 0.4 degrees would be small, but 0.4 radians is not that small. It's 22 degrees. Look at the question. Okay. So much for that. Now we can go back to our problems with the circles and find the arc lengths. Okay, so here's where this lesson is going from here on out. Okay, we're going to talk about 3 things regarding this circle. We're going to talk about the length of that arc, that's S. We're going to talk about the area of that pi slice, that sector area. And then we're going to talk about an object moving around the edge of the circle and its speed. Okay, so now that we know what radians are and how to get them, we can do lots of examples. So remember, the formula is S equals R theta. It's up above. If I said find the arc length of a central angle of 100 degrees if the radius is 10, and let's just make it 10 centimeters. Here's what's going on. You've got a circle. The radius is 10 centimeters. We're talking about a 100-degree angle, so that's like something like this, just past 90. Okay? And we're wondering what this distance is right here. But we call it S. Okay, so this is a simple formula. If the radius is 10, then we can just put 10 centimeters here. And the central angle, that was 100, right? So can I just do that? And then that'll be the answer, right? No. 1,000 degree centimeters. Okay, something's wrong with this picture. First of all, there ain't no way that this length is 1,000 of anything. Well, maybe 1,000 of something, but it's certainly not 1,000 centimeters. And I don't even know what a degree centimeter is. What is a degree centimeter? I don't know. The problem with this is I had a warning up here in purple that says that this angle is supposed to be measured in radians. Degrees are never invited to this formula. You cannot put in 100 like that. That was wrong. Okay, so I did that on purpose. You can't put 100 there. You have to put 100 times pi over 180. There we go. Okay, so you can actually just reduce stuff. Like this is just 5/9. And so this comes out to 50 pi over 9. And now this is us centimeters. You might say, hold on, Mr. Shore, now it's radian centimeters. Radians are the invisible unit. So you don't even have to write radians if you don't want to. Okay, let's try a different one. Let's say that I told you find theta. So this is a little bit different. Use the same formula, but this time it's theta that's unknown. So let's say you're given the radius was 10, and let's say that the arc length was 24. You're trying to find this angle here in the middle. See? Well, you still get to use S equals R theta. And this time let's be nice to the imperialists. Let's use inches. Okay, we've been bashing the imperial system for a long time in America, trying to convert to metric, but let's go inches. So we have this formula. We put in the 24 on this side this time. The 10 goes here. The theta we don't know, and you divide, and you get theta equals 2.4. The central angle is 2.4. 2.4 what? Degrees? That's an angle. Radians. This formula, not only do we plug radians into it, but we get radians out of it. Okay, so you end up with 2.4 radians. If you're curious what that is in degrees, you can convert it. I could also come up with an example where I give you S and theta and have you find R, but I don't want to get carried away. Now let's go talk about our fourth objective. Yes?
So if you said...
There's a button for it. When we do our Q&A for the homework, I can show you where all these buttons are. There's a DMS button, there's all that stuff in there. But it isn't that much faster than just doing it by hand. You know, divide by 60 twice. Like, I don't know, I don't really see the point of all those special features myself. Okay, our next objective is to find the area of a sector. Okay, so let's just revisit geometry days. So a sector is when you take a slice okay, and you shade it. So you probably know that if you've been doing any SAT prep or something, you see that word a lot in your prep classes. So this is called a sector. So it makes sense to want to be able to find the area of that. But listen, you can use your common sense here. The area of the sector is going to be some fraction of pi r squared. It is some fraction of the total area, right? What fraction? Well, it depends on the central angle. right? It depends on how much angle you want. Like we said before, if the angle at the center is 180, it's half the area of the circle, and so forth. So it's basically central angle over 360 again. This is what you would have used in geometry class. Very similar to the formula I had up a few minutes ago. We're not going to use it though, because we're not using 360 degrees. We'll be using radians. What is 360 degrees in radians? 2 pi, right. So we're going to be using, instead of 360 here, we're going to put a 2 pi there, see? And you'll see what happens. The pi cancels out, and we end up with this formula. Area equals central angle over 2 times r squared. Most people memorize this formula right here. Sector area is 1/2 r squared theta. And we have the same rule we had last time, that your angle has to be measured in radians. Okay, so that is not optional. You have to measure the angle in radians. Okay, same warning as last time. Radians only. Okay, so let's try an example real quick. Let's say I said find the area of the sector and let's just say that this is 200 degrees central angle. And the radius, let's say, is 3 what? I don't know, 3 feet. We want to find the area of that sector. So we want the area of this thing. Okay? So you have a formula now. You just do area equals 1/2 r squared theta. R is the radius. You just put in a 3. Be careful with theta. They gave you degrees. Watch out. You have to put 200 times pi over 180. Remember, degrees are never invited to the formulas. So you have to do that. And then you can just simply reduce this to be 10/9. There's another 9 out front. That 3 squared there. So you just end up with 5 pi as an answer. 5 pi what? 5 pi square feet. It's pretty common to have pi in your answer. But I'm just curious what 5 pi is. I know it's roughly 15 point something. It's 15.71 square feet, if you want to sort of understand it better. Or I could give you the area and have you find the radius, or I could give you the radius and have you find the central angle. It just depends on what I feel like giving you, right? It's a formula with 3 variables. I give you 2 of them, you find the third. Okay, the last objective is to talk about motion. Everything we've done is static. Nothing's moved. We've measured the arc of a circle, the area of a sector. We have not done anything in motion. Okay, so let's see if we can understand linear velocity versus angular velocity. Okay, so what does this even mean? Well, does anyone in this class drive? Does anyone have a car, or they drive their parents' car? Okay, so on your dashboard you have a speedometer, an odometer, and a tachometer. 3 different dials, okay? The speedometer tells you what? Your speed, right? Speedometer, measures speed. Then we have the odometer. What does that measure? That's how many miles you have on your car. Or if you're taking a trip, it'll tell you how many miles that trip was after you're done driving it. What is the tachometer? Tachometer. Tachometer. What is that? Okay, that's the one that says RPM. Okay, so maybe you've had your car in neutral and you've accidentally stepped on the gas and it goes, right? Well, the engine's working really hard and you're not going anywhere. The engine is cycling, right? It's running through its process. And if it says 2,000 on the dial, it means it's doing 2,000 revolutions per minute in the engine, even though you're not going anywhere, right? So you hear phrases like RPM, you know, what does that mean? It means rotations per minute or revolutions per minute. Same thing, okay? So is it the same thing? If you spin a wheel, right? Let's say you take a wheel and you spin it once. You might say, oh, I turned the wheel once in 2 seconds. Is that the same thing as telling me how fast this little point is moving in space? No. There's two different ideas for speed. Okay? So here's what I'm saying. If you take a circle and you look at the static case, we know that r times theta gives us s. Right? We just wrote that a few minutes ago, s equals r theta. If you put this in motion and you talk about something moving along the edge of a circular path, so it's actually moving now, you might not be interested in s. You might be interested more in a speed, which would be distance over time. So this might be like s over t would be your speed. This would still be r. And this theta here would be changing, see? So this would be basically theta over t. So you could write the same formula, instead of s equals r theta, you could just basically divide by t like this. And you get a brand new formula that regular speed, we call that v often, is equal to r times angular speed. It's kind of like the rate at which it's turning, and we often call this omega. Okay, let's talk about what the variables mean. This means speed just as you've always known it to mean. Some people call it linear speed. Some people call it tangential speed. There's many names for it, but it's just speed like you normally think. Feet per second, miles per hour, whatever. Light years per whatever. Okay? Now, this and this is obviously a radius. What is omega? Omega is your angular speed measured in radians per time. So this was a little bit harder to grasp because we're talking about something moving, and I can't really draw something literally moving for you. So what I'd like to do is just do an example. Suppose an ant is traveling on a circle of radius 10 centimeters at a rate, and let's make the rate an angular rate, how about at a rate of 2 RPM? What is the ant's speed? Well, you can tell from the way the question's written that we're going to be using this formula. We've had several formulas today, but certainly this is the only one that involves motion at all. And you will see this in physics if you haven't already. So obviously the radius is 10 centimeters. They're asking for the ant's speed, so I assume they're not wanting to give us v, right? What am I going to put here for omega? Well, it says 2 RPM. What does 2 RPM mean? What does RPM stand for? Revolutions per minute. Is that the same thing as radians per minute? No. Okay, yeah, so you can't put 2 here in the formula. You can't put revolutions per minute into my formula. You can put radians per minute. Okay, only radians are invited to the formulas. So what I have to do is figure out what 2 RPM means. A revolution means 2 pi radians. We said that earlier. So 2 revolutions per minute would be 4 pi radians per minute, is what it would mean. So we would just basically think of this as 2 rev per min. If you multiply this by the fact that there are 2 pi rad in 1 rev, you see that this is actually 4 pi radians per minute is what goes in the formula. Okay, so this just turns out to be a speed of 40 pi centimeters per minute. Don't write the radian is invisible. Supposed to ignore it. And 40 pi is 125.664. So we have basically 125.664 centimeters per minute. The hardest part about it is figuring out that when they said 2 RPM, what they meant was twice around a circle, which is 2 times 2 pi, and you had to put 4 pi in for your angular speed. All right, and that concludes the lesson.